All right, thanks for coming to the new session that used the name Berkeley Data Analytics Stack, which is something some of you probably never heard of. I actually think we make a big mistake in the way we marketed this talk. But here we go. So my name is Reno, and I'm a PhD student at UC Berkeley. And this is my colleague, TD. In case you can't figure out how to pronounce his name, it's a much easier shortcut, just called TD. And I'm going to give sort of a quick overall introduction to the Berkeley Data Analytics Stack first, covering some of the components in a very high level. And then TD will take the second half of the talk about one of the more components and dive into it. The clicker didn't work. Bear with me for a moment. All right, here we go. So in the past few years, we've been building this new generation data analytics stack at UC Berkeley Amp Lab called the BDAS. If there's only one takeaway today, that's how you would pronounce this name again. There's a lot of pronunciations happening here. It's all really started with one central component called Spark, which is a new MapReduce-like engine running on in sort of part of the Hadoop ecosystem. So it's compatible with the Hadoop storage inputs, and it also runs and can be managed by resource managers for Hadoop. And on top of Spark, we have been building a number of other systems, including the Shark SQL system that's compatible with Apache Hive. And then there's a Spark streaming system that basically runs streaming workloads on top of Spark. And then there's a newer framework called GraphX, which is a graph processing system and ML-based, focused on machine learning. In this talk, we're just going to focus on the upper layer of the stack. So we're not going to talk about HDFS or how you're going to run stuff on Yarn and Mesos. And Spark started about 3 years ago and was initially open source. In 2002, we open sourced a newer component called Shark, which is the SQL component. And then earlier this year, the streaming component of Spark is open source. And I think last week, Spark officially joined the Apache Software Foundation's incubation program. So we're donating the project to the sort of wider community. And in the past year or so, we have really seen significant traction to the project. For example, we opened up one of the official training for Spark at UC Berkeley called Amp Camp. And it was sold out in person. The in-person seats were sold out in less than a few days, and they opened up live streaming, and over 3,000 people actually watch up the streaming online. And we also run a regular meetup group in the San Francisco Bay Area. There's over 800 members. If you're from the area, I encourage you to check it out just on meetup.com. For the past release, we have seen over 60 developers contributing code to the project from 17 companies. There's a lot of companies really starting to pick up the stack and use it. And so I just listed some of them here for your show. And but the best news is probably we were mentioned in the one of the keynote delivered yesterday as going beyond MapReduce in Yahoo, and Spark was mentioned as one way to do iterative interactive analysis of data. But I think the strongest evidence is in 2012's Hadoop Summit. In case you can't see it, it says Spark and Shark, high-speed in-memory analytics over Hadoop and Hive data. And we were in the future of Hadoop track. So we were the future. And this year, you might have realized already, we're actually part of the Hadoop economics track. So we're no longer just the future now. We're actually part of the ecosystem. Thank you. And this was a joke, by the way, in case you didn't realize. So now, let me go into sort of the first part of the talk, which is to introduce you. Some of you, can I get a show of hands? How many of you have heard of Spark and actually know? Whoa, OK, good. Can I get a show of hands? How many of you actually heard of a similar talk before? A high-level overview of Spark already. OK, good. So I don't have to skip half of the talk. So Spark, at a high level, is a fast, expressive cluster compute engine that works well with Apache Hadoop. And it mainly focuses on two things. One is to focus on improving the performance of your jobs. And it does this by both in an optional in-memory computation primitives it provides, and also supports a general DAG of execution environment, so going beyond the simple, strict two-phase map and reduce. And also the other part, which I think is equally important, is improve actually the programmability and usability of writing this job. So it makes your program faster. And it does this by providing an upper, sort of a higher level API, which I'll cover in a bit. And when I talk about performance, it can be up to 100 times, sometimes even more, faster than Hadoop MapReduce when you run stuff in memory. And even when you run against data on disk, it can be substantially faster too. And often with much less code required. And why a new framework other than, even if you run 100 times faster, why can't we just make MapReduce run 100 times faster? I think, so MapReduce really, when it was introduced in probably 2004 by Google, it significantly simplified the way you program large clusters, to use large clusters to process a huge amount of data. And when it got popular, people demand more, right? And I think this goes into 3 dimensions in terms of demand. One is the complexity of analytics is increasing. So you want to do multi-pass algorithms like machine learning, graph processing, or even a simple SQL statement might get decomposed into multiple stages of MapReduce. And you want the execution engine itself to be aware of the multi-stage nature of your job. And people demand interactivity too, so you want to run ad hoc queries. And the other one is you want your queries and your jobs to be more real-time so you can process streaming data in a fast fashion. So Spark solves all of this above problem, so with a key idea called RDD. Again, I don't think you need to remember the full name, just remember the part RDD. And RDD is really just a distributed partition collection of objects, and that is immutable. So it borrows a lot of the ideas from functional programming, and you can create new RDDs either by referencing some files on a persistent storage like HDFS, or you can create a new RDD by applying a transformation on an older RDD. Transformations include operations like map or reduce or join, and all of those. And RDDs are fault-tolerant, so it can be recreated automatically upon failures, which is a key requirement on large clusters. And we provide, right now, 3 APIs in 3 different languages, both Scala, Python, and Java. And you can use it not only you can run your programs on top of an existing MapReduce cluster, but you actually write Spark jobs in interactive shell in both Python and Scala shell. It's no Java shell, unfortunately. And there was a lot of the dry. Let's go through one example. And the example here is, let's say I have some log files stored on disk, and I want to analyze those log files. In this example, I'm using the Scala API. But really, even if you don't know Scala, I think you can pick it up, the high-level ideas very quickly. So in this way, I'm going to first create a lines RDD to reference some text files on HDFS. And then I'm going to create, let's say my log files are only, all the errors start with the word error. So I'm going to create a new RDD called errors by applying a filter operation on the lines RDD. So lines is my raw input data set, and errors is sort of a filter data set only contains where lines that start with error. And the highlighted red part here indicates a closure or anonymous function or lambda function, depending on what context coming from in RDD. So what it does is it applies the underscore start with function. Underscore in Scala means it's the first argument. So for every line, I'm going to test whether it starts with the word error. If it starts with error, I'm going to put it in the errors RDD. And then there's this interesting function called .persist, which marks the data structure as being, Spark should try to keep this data structure in memory across the cluster as much as possible, because I'm going to repeatedly query it. And on the right here, to your right, there's a tiny cluster with a master node and 3 workers node, very similar setup to your Hadoop MapReduce. But nothing really, so this whole program runs on the master right now. And then, not very familiar with the clicker. The whole program runs on the master right now, and actually no execution is happening right now, even though conceptually we are creating new data structures or new RDDs representing our data. But really, everything is lazy here. And it's all just metadata management. The Spark engine, up until this point, we're just telling the Spark engine, this is the way I could recreate the data. For example, errors or lines. And now, the next one we're going to do is, let's see how many error messages contain the word full. And there's an operator. So you could call a filter operator which again is just another closure that checks where the string contains the word full. And then you call a .count operator. And the count, in Spark's context, is what we call an action. So when user executes an action, the user demands something back. In this example, the user wants to know, he wants to get an integer back to tell me how many error messages contain the word full. And because you have an action, you actually want the result. Spark will now lazily actually evaluate the results. So what's going to happen is the master is going to query the HDFS to find out where all the blocks are in HDFS. And it's going to start launching tasks, schedule them onto the nodes based on locality, and compute the number of counts on each of the partitions, and then merge the counts and send the results back. But because we mark the errors as persist, while it's executing the count example here, Spark is going to build up in memory representation of the errors RDD across the cluster. So now there's some in-memory blocks labeled as purple here. And the next time, if you run another query, for example, full wasn't a prom and bar is a new thing you're grabbing for, Spark's going to launch the task schedule based on the in-memory blocks locality and just query the memories directly. And this example, you could do a full Wikipedia grab in less than a second on 20 nodes. And if data on disk, it takes a minimum of 20 seconds, which 20 seconds is still pretty good. For example, it takes 20 seconds to just launch a job in MapReduce. But 20 seconds is not exactly interactive. And Spark really gets you with in-memory computation primitive, gets you to the sub-second interactivity you want. And this really scales up pretty well, too. For example, we've done testing on the terabytes of data, and you can actually grab the terabytes of data in 5 seconds in memory across a cluster. And the other part I talk about, in addition to the performance, very important part is the expressive API, the high-level API. We beyond much the simple map and reduce APIs provided by Hadoop. And it includes a number of things. For example, I already showed you filter count. You can do sort directly out of the box. You could do reduce by key, and sampling is a first-class primitive. Also, you could do join as a first-class primitive as well. And well, why, right? You might have workloads there. You think this might not apply as much to your workload. But one key motivation for this work is actually machine learning. A lot of machine learning jobs are iterative just by nature. They're running the same computation over the same data set over and over again until some convergence happens. And so this is one example, actually 2 examples running Spark using logistic regression algorithm, which is a way to do classification, and then the k-means algorithm to do clustering, comparing the performance. And as you can see, we could run jobs in less than a second in LR case, and in the k-means case for 4 seconds in every iteration. This is substantially faster than what you can achieve with Apache Hadoop MapReduce, because we don't have to go to disk every time. And one other thing I want to point out is it's not just also about in-memory. It's also the fast nature of the execution engine itself. Think about, even if you run Hadoop MapReduce against a bunch of RAM disk, you won't get a 0.96 second per iteration runtime, because again, it takes a long time even to just schedule those jobs. So it's really a number of advanced features along with a memory computation primitive that enables this super fast runtime for machine learning algorithms. And again, this one I show you the simple example of running Spark in this Java API and the Python API. The Python API looks very similar to the Scala API, except uses Python's lambda and syntax. And the Java API is a little bit more verbose. I think that's probably partially the reason Java doesn't have a shell. But if you're sort of much more comfortable writing Java, this is it's good to know this API for it. And we built 4 other components on top of Spark that's sort of either has already been released or very close to getting released. I want to go through 3 of them very quickly: the Shark SQL project, GraphX, and the ML-based machine learning project. And then I'll pass on to TD to do the second half of the talk on Spark streaming. And GraphX is, so graph processing is gaining a lot of traction in the past few years because of the rise of social networks. And you can actually model a lot of problems using graphs in the inference world. But data parallel systems like Spark or Hadoop MapReduce is not very good at capturing the dependencies and complex data structures of graphs. That's why we built GraphX, which in our mind combines the data parallel frameworks like Spark with graph parallel frameworks like Prego, Giraffe, or GraphLab. And it allows you to run graph analytics. Think about it as a framework on top of Spark. They allow you to run Spark operations and GraphLab and Prego operations in the same engine. So you could use Spark to do ETL, but without leaving the same worker process, you could use those data directly to run graph computation. And then you can use Spark again to consume the output of your graph computations. The interactive shells for both Spark and Python and Scala. It's very easy to program, so inherently a great way to, I think, a huge advantage of Spark. So we actually, its API itself was able to express both the Prego interface and the GraphLab interface, about 20 lines of code. So we exposed the same abstraction. And then you could implement PageRank literally in 5 lines of code in it. And it's coming this summer very soon as a new module in Spark. And the other part is ML-based. And the motivation is, what do you think right now, if any of you have tried to implement machine learning algorithms, for example, if I want to build for X, and this is what you have to do right now. You have to learn the internals of how the algorithms works. And then you have to potentially learn an execution framework, Spark, Hadoop, R, any of this, and implement a number of different algorithms to get a feel of it, and then use and then test the parameters, see how you can best run this job. And then at the end of the day, it's really too hard. You just go to an expert. So the idea of an ML-based project is we want to bring together a group of people, since we're from academia and to be more forward-looking, so we're bringing a group of people both from the machine learning side and from the system side who knows how to build systems, and there's people who knows how to write algorithms, and bring them together and then create this new way we call declarative machine learning. So the user now specifies, I just want to build a classifier for X. And ML-based is going to figure out what are the possible best algorithms you could run and what are the parameters you can tune, and the system will figure out the rest of the things. And as the first step, that's a very admirable goal, and it's going to take time to get there. But as the first step, we're getting together this group of collaboration, and I think the collaboration will lead to a collection of scalable, high-quality machine learning algorithms implemented as a library on top of Spark, which will be released also this summer. And the next one, which probably glance through, is Shark. But it's a very high-level overview of things, and you're welcome to talk to us offline too, to more about it. Shark is essentially a SQL engine to Spark. So it's what Hive to MapReduce, that is Shark to Spark. It's even compatible with Apache Hive, so you could run your Apache Hive query language, your Hive UDFs, your Hive scripts, and it even reads directly from a Hive metadata, and it can execute those queries in their cluster. So it's sort of a drop-in replacement for Apache Hive, and you don't have to change your queries or data. It can be substantially faster for a number of reasons. One is they actually rely on Spark as a fast execution engine. So you can actually do low latency query in sub-second queries. And the other one is it actually, leveraging Spark's another in-memory primitive feature, you can dump your data in memory across a cluster and do repeated query on those data very quickly. And the other cool thing is actually the execution engine, because we're building on top of Spark, will allow you to run SQL and data parallel programs in the same engine directly. And just want to, I don't have a lot of time in this talk, but I always like to show this real-world performance. I got about 2 terabytes of data from a company doing video analytics, and I got 3,000 queries from the Hive warehouse for the past 2-3 years. And so I ran some of the most frequently run queries on their Hive cluster and against the Shark cluster I built up. And this is just the performance comparisons. And it's enough to say it's actually, so in all cases, these 4 very frequent queries they run, we were able to bring the time from over 50 seconds to less than a second in almost all cases. And even when data's on disk, it's substantially faster too. And so that this experiment was done in the context of a paper publication we have done. And since then, we actually tested some new things. For example, we have this new big data benchmark another guy is maintaining that just tests the performance comparisons of different frameworks. And Shark actually performs fairly well. Because in some cases, you can make Shark worse than the other frameworks. But hey, it's a marketing slide, so gotta include the best one, right? But really, the idea is Shark has a lot of benefits that other frameworks don't support. For example, direct replacement for Hive. It supports the Hive UDFs, Hive QL, as well as integrating better with underlying frameworks so you can run both machine learning and SQL in the same engine. But despite all those more, I think, the richer features, it still perform, in terms of performance, very competitive with the latest tools coming out of other companies. And I didn't even bother including Hive because they would make the chart a little bit hard to read. All right, so now I'm going to pass on the talk to TD to talk about Spark streaming.
Hello. Hello. Okay. Thanks, Reynold. Okay. So Spark streaming. So this is one slide summary of what Spark streaming is. And I'm going to go into detail from again the next slide. But what it basically does is basically it extends Spark's functionality to handle large-scale stream processing as well. And it can receive data directly from Kafka, Flume, Twitter, and it's since it's built a very fast and efficient programming engine, processing engine like Spark, it is naturally fast, scalable, and fault-tolerant due to the properties of Spark's RDDs that I'll talk about soon. And in terms of the functionality in the API, it provides a very simple, rich batch-like API to express all your streaming computations in. And so it allows you to express your very complex streaming computations in a very simple manner with very few lines of code. You can Git provides stateful stream processing directly out of the box, which makes it easy for doing a lot of streaming computations. And since it's built on Spark, it's very easy to intermix batch and stream processing together in the same program. I'll explain all of these in the next slides. So the motivation of why we built this Spark streaming is that we looked around and we saw that there are a lot of applications out there which requires real-time or near real-time data processing, like social networking trends, like you want to figure out top trends on Twitter, or in general social networks, statistics on websites, or real-time load data, whether your system is performing correctly or not, intrusion detection systems, you name it. And we've tried to figure out why, in building a framework that allows you to do stream processing in a scalable manner, what are the key challenges that one needs to solve? And the top two definitely being that these workloads require large clusters to run, and they need end-to-end latencies of something like few seconds. Not all of them need millisecond level latencies. A lot of near real-time applications are fine with few second latencies. And so that is what we target. Cluster faults may happen. And another key requirement that we felt was tight integration with batch processing systems. Now, let me explain that. So we found that there are many environments in companies, in wherever you need streaming data analytics, that in these environments you need to process the same live streaming data later as post-processing using batch computations as well. So it's like you're doing the same computation once in your live stack, again later in your batch processing stack to generate, let's say, monthly reports, etc., where you process a lot more data together than what the live stack processes and generate more aggregate reports and numbers. Now, the problem in the current world is that there doesn't exist a good framework that can achieve both, that can handle large volumes of data like that is necessary for batch workloads, as well as provide really low end-to-end low latency that is required for streaming workloads. So it doesn't exist a single framework that can do that well, and which was our motivation. And why is that a problem? Because that means that as developers, you have to deal with two different programming models of two different frameworks, one for dealing with streaming data. Let's say you want to deal with streaming data using Storm. So you have to write your program once using Storm, and then you want to generate reports on the collected data. You have to write the same program again using, let's say, Hadoop or some other batch processing system. That means your implementation effort is doubled. You need to deal with double the number of bugs. Leave aside the basic problem of dealing with two different programming models, which may or may not make, you have to interpret your algorithm in two different ways. Not a good idea. And if we take a look at existing streaming systems, Storm, which is a very good streaming system and is very popular, in terms of fault tolerance guarantees, it is a bit tricky. So what Storm guarantees is that it replays records that haven't been processed by the system. So what that results in that the system guarantees that every record will be processed at least once, not at most once or exactly once. So what may happen is that suppose you're maintaining a count of all the events that you have seen over a period of time. This property may easily lead to double counting of your events. Furthermore, if you want to do any kind of stateful stream processing, where basically you want to keep an in-memory state that you continuously update as you get events, that in-memory state may be lost if the node on which you're running the Storm topology dies. What do you do then? Your count may suddenly get reset to 0. To solve that, well, Trident was written, and which uses transactions to update the state to make sure that the state it guarantees exactly one's processing, exactly one's semantics, and the state becomes fault tolerant. But you're doing an external transaction to an external system, Zookeeper or some other system, to do that transactional state updating. And the moment you keep contacting the external system, it harms your throughput. So it is a decent idea, but we believe that we can do better. And neither of these systems integrate very well with batch processing systems, which I hopefully convinced you that is a very strong requirement in today's world. So that led us to Spark streaming. And the processing model that we use in this system is called discretized stream processing, where we run a streaming computation as a series of very small deterministic batch jobs. Basically, let's say you have a live data stream. Your Spark streaming will receive the stream, divide it into batches of x seconds. X you can configure, send the data to Spark, and Spark will process the data and give back the results in batches. And now to reduce the end-to-end latency, the challenge is to reduce the batch size, because smaller the batch size, smaller is the end-to-end latency. And we can reduce the batch size to as low as ½ second to give an end-to-end latency of 1 second. And that is because Spark is a super optimized engine that can do run, map, reduce or jobs at sub-second latencies. This enabled us to do run a streaming workload on a batch processing system like Spark. And therefore, there's a natural potential for combining batch and stream processing together. Let's see how does a program in Spark streaming look like. So let's say you want to process the Twitter stream, and so what you will do is you first create something called DStream using your Twitter's username password, and this DStream is basically a sequence of RDDs representing a stream of data. To remind you what RDD is, it's basically a distributed partitioned collection of objects that may be stored in memory. So what happens underneath when the system computes this, the system runs this Spark streaming program, is that as you receive data from the Twitter streaming API, the data is chopped into batches. It is stored in the memory of your cluster as RDDs. And then you can apply more functional style transformations, like for example in this case, we are applying a flat map, which is a one-to-many operation, where from every status update, we want to get the list of hashtags from it. And that gives you, and flat map is a transformation, and that gives you a new DStream, which is basically a stream of hashtags. And underneath, the system basically creates new RDDs for every batch of data, RDDs that consider only the hashtags. And this all happens underneath when you actually run the Spark streaming program. And then finally, what to do with the data. So as for example, you could save each batch of data as Hadoop files. And that is how you do it. You specify save as Hadoop files, give it a directory in HDFS or any HDFS compatible file system. and the system will underneath save each batch as an HDFS file. It will take care of itself. Or you could do something, anything arbitrary with the data. For example, this for each operation allows you to specify any arbitrary operation with each RDD. So what you can do is take the data of each RDD and push it out to Redis, let's say, or you can push it out to Cassandra, or directly update your web server front end to show real-time statistics. You can do whatever you want, and it can be done distributed across the cluster. So you have the freedom to do whatever you want with the processed data, and that is very powerful. Out of the box, we also provide this window-based operations, where it allows you to aggregate data and do computations over a whole window. So let's say you want to process the hashtags and count all of them together, but over a window of 1 minute. So count all the hashtags, like word count, over a 1 minute window, and that's how you do it, and give the result every 5 seconds. And so underneath what the system does is basically a sliding window, and the sliding window is obviously defined by the length of the window, in this case 1 minute, and the sliding interval, how much it will slide every time, in this case 5 seconds. So we provide this out of the box that is helpful in a lot of cases. What we also provide is the ability to specify arbitrary stateful computations. For example, let's say you want to process the Twitter stream, and for every user on Twitter, you want to maintain what mood he or she is in. I know it sounds a little creepy, but let's say you want to do that. And so what you need to specify is basically a function that defines, take the previous state, take the new data, and how do you generate the new state. So in this case, take the previous mood, take the new tweets of that user, and generate the new mood. And then using this operation, update state by key, the system will apply this function over all data in a distributed manner. The system will take care of itself. And since all of these computations are based on RDD transformations, it automatically provides exactly one semantics, because RDD by nature, it is fault tolerant. So if any of the node dies and part of an RDD in memory is lost, it can recreate itself. The system will recreate itself automatically, and you get exactly one semantics for any transformation that you apply on DStreams or on RDDs. And here is the cool thing. So it allows you to arbitrarily combine streaming and batch computations. So let's say you have this stream of Twitter, and you want to join the tweets with HDFS file that you have with the spam hashtags in them, because you want to filter out the spam hashtags. So you want to take every tweet RDD in the DStream and join it with a spam hashtag file, filter it out. And you can do this very easily in this DStream abstraction using this API transformation called transform. And the system will take care of running these arbitrary RDD computations inside transform, because the whole system is running on Spark, which naturally understands RDD. So this is doing this natively in any streaming platform is, in this current state, not very easy, but Spark Streaming kind of provides it out of the box, which allows you to do a lot of complex computations, which is harder to do in existing streaming systems. So out of the box, we provide creating DStreams out of Kafka, Twitter, HDFS, Flume, and even raw TCP sockets if you want to write your own input source. And you can write, and it's a very simple API to write your own input source from any input source. I mean, for example, people have tried sending raw bytes over UDP and things like that. It's very simple to implement that. Let's talk about performance, of how well does this perform. So we actually tried Spark Streaming on 100 text streams running on 100 EC2 instances with 4 cores each, and in aggregate it could process 6 gigabytes per second. That is in total 60 million records per second, 600,000 records per second per node, and all with an end-to-end latency of sub-second, of 1 second latency. And you can, and that is for, that is for the grep workload, where you will basically you're filtering by a particular keyword and counting how many records matched. For something like word count, where you count the number of words in the text stream, the throughput is a little lower, but still it's in the 30 million records per second. It's a little lower because it's a slightly bit more computation. There's map and reduce, kind of like map out here only. And as you can see, you can configure what is the latency that you are okay with, and accordingly you will get slightly higher throughput, as you can see with 1 second, 2 second latencies. So the bottom line is you get both high throughput as well as low latency from a system that is using the same programming model as Spark, effectively. We also compared it with the existing system Storm, and we basically wrote the same grep and word count using the Storm API, and we optimized it, and we found Spark streaming, it could do 670 records per 1,000 records per second per node, whereas Storm was limited to 115. And we believe that that is because of the way Storm handles the fault tolerance, that it basically sends acknowledgements on a per record or a per small batch basis, which is a small batch, whereas since we are keeping track of data at the scale of RDDs, due to this tracking metadata is much lower in our case, thus allowing us to achieve much higher throughput. Fault tolerance, this shows that, so this is the processing time of each batch of data. I think it was 2-second batches running on 10 nodes. And these 2-second batches took around 1.5 seconds on average to get processed. And here one of the node died, and it could recover within a second. It was so very fast to recover because all the data that it has received is in memory, so failure recovery is very fast. We also tried real applications, in this case traffic sensing. This is a research project back in Berkeley where we do complex machine learning algorithm, in this case Markov chain Monte Carlo simulations. Don't ask me what that is. But it's a very CPU intensive, and you actually need a large cluster to do useful computations on hundreds of GPS observations per second. And we implemented that on Spark streaming, and you can see that the system scales very linearly with the number of nodes in the cluster. We tried, I think, up till 80 nodes, but we could have tried more, but we just didn't. So also, this is almost my last slide. So if you look at the program that you write for Spark to process a HDFS log file, and a program for Spark streaming to process a live Twitter stream using DStreams, the program looks pretty much exactly the same. The only difference being here you open a Hadoop file, here you open a Twitter stream. The rest of the things is pretty much the same. So what this allows you is to use the same code base, using the same programming model for both your batch processing and stream processing workloads. And this is a very powerful thing that we believe will give a game changer in your data analytic workloads. Finally, to conclude, we're building this next generation of data analytics stack that handles both speed and complex functionality to make complex functionality easier for developers. You can get more information on sparkproject.org. So if you want to try out the BDAS stack or different aspects of it, there are hands-on tutorials on the AmCamp website. So AmCamp is this, I think Reynal already mentioned, AmCamp is this tutorial that we host, that we hosted last summer. And we're going to host again this summer on August 29th and 30th, where we actually walk you through the process of starting a Spark cluster and running simple programs on it. And so if you're around in the Bay Area, then definitely come to AmCamp 2. The location will be announced shortly. So keep looking at amcampberkeley.edu website. And we also have a very active Spark mailing list. You'll all find all that information on sparkproject.org. And go ahead and try it out. You can try it out on your local machine. You can just download the code and immediately start writing code. You can take the same code and very easily run it on an EC2 cluster. We have the instructions of setting up an EC2 cluster. It can be set up in 5 minutes, and so in 5 minutes you can start running your code on cluster, on Spark, and for the Spark streaming and everything. Thank you. Questions?